Good morning, good afternoon, and good evening, our viewers. Welcome to our lesson in chemistry, and that is Hess's rule. As before we progress, I would like to welcome you to our YouTube channel at Steve Getao 3660, where we teach concepts in chemistry and also in mathematics. We shall be launching our website soon with the handle Educational Resources Center. Welcome to our lesson today. The first thing is this subtopic or this area is drawn from the broader topic that is thermochemistry. In this particular topic, we look at various enthalpies or various heat changes. Majority, that is heat of neutralization, combustion, and so many others, can be obtained via experiment. Talk about heat of displacement. However, we have one heat change, that is heat of formation of a compound. This must be determined from the theoretical values, and that's what we have today. Hess's law at times has been challenging to runners, especially in the calculation, and that's why today we look at it in great detail. Number one, let's define what is Hess's law. Hess's law of constant heat summation states that the heat change in converting some reactants to products is the same regardless of the route followed. And we shall be able to see this one in form of an energy cycle in a real calculation. So let's put that one down. We say Hess's law states that the heat change in use or the heat change in converting reactants to products. So we can put in the word here, involved. The heat change involved in converting reactants products is the same regardless of the route followed. Regardless of the route followed. We can explain that one in a simple language. Take for example, I may use this space here. We have a product A reacting with the product B to yield an intermediate product C. However, product C later on is converted to product D and possibly E. Now you realize that A can also be converted to E, B can be converted to D. So we have an energy change here, H1. We have an energy change here, H2. At the same time, we are saying that we can have energy change, which you can label it 3, and this is 4. So what are we saying? If we convert our products A and B we convert our reagents A and B to be product ED by following this route, which we are calling route 1, the energy change is the same where A and B are directly converted to be E and D. this is root 2. And that means delta H1, heat change 1, and heat change 2 are equal to heat change 3 and heat change 4. So this is the theory behind Hess's rule, that the heat change in converting this reactance product is the same regardless of the route followed, and we sum where 2 are engaged. So that is the theory behind Hess's rule. Now, it is used in calculating heat changes, say heat of formation, which may not be easily determined in a laboratory setting. For example, we are required to determine the heat of formation of ethane, from this information. That we have carbon, which for ethane to be formed would need to react with the hydrogen, so that we have ethane. Ethane is carbon 2, hydrogen 6. So what does it mean? It means we shall require 2 carbon atoms here. We shall require 6 hydrogen atoms. Where will they come from? They will come from 3 molecules of hydrogen, totaling 6 atoms. Now, when this is formed, we may not be able to know the heat change. The heat change delta H1 is not known. We are not provided here. What are we provided with? We are provided with the heat change when carbon undergoes combustion to yield carbon 4 oxide. So when carbon reacts with oxygen, CO2 is produced. However, we need to be very careful here. We have 2 carbon atoms in the reaction. In the formation of ethane, we have 2 carbon atoms. However, we are told when 1 carbon atom undergoes combustion, it releases 394 kilojoules for every 1 mole. So we can read it as when 1 mole of carbon undergoes combustion, it releases 394 kilojoules. What about when 2 carbon moles? When 2 moles of carbon undergoes combustion. So that energy change will be, we need to double that, negative 394 times 2. That will give us our delta H, we can call it delta H3. So this is very important. Balancing for oxygen will come in later. 2 moles of carbon yield 2 moles of CO2. That means we shall need 2 moles of oxygen. Let me put this clearly. So the energy change here would be negative 394 times 2. We shall come to that when we shall be calculating H3. Let's look at hydrogen. Hydrogen reacts with oxygen to yield water. So we shall have water here. However, we have 6 atoms. We must be able to account for them here. So we have 3. And that means where 1 mole of hydrogen releases 286. So this will be negative 286 times 3, because we shall be reacting 3 moles of hydrogen. If 1 mole yields 286, 3 will yield how much? This will be our value for delta H4. We need also to balance the oxygens and say this one will require 3 mole, that is 3 and that is 3 over 2 moles of oxygen. 1.5 moles of oxygen. Now the final bit When ethane undergoes combustion, it yields these two products. It is able to yield CO2 and water. In ethane, 1 mole of ethane, there are 2 moles of carbon, and that is what we have here. In 1 mole of ethane, there are 6 hydrogen atoms. That's what we have here. So how much of oxygen do we require? We require 4 plus 3. That makes 7. And that comes to be about 3 all over 2 oxygen atoms. Let us see if that is going to be okay. We need 4 plus 3, that is 7. So that should be 7 all over 2. 7 all over 2 oxygen atoms, that gives us 7. So we have that one done, and we can label this as delta H4. Let's come to this one. This will be our delta H4, this will be our delta H3, this will be our delta H2, meaning delta H1 is unknown. What is that? The energy of formation of ethane, and we shall look at the definition to that. So, going by our earlier reasoning, we are able to see that we have 2 routes. The first route follows this path. It actually follows this kind of a path, whereby we have delta H1, this one, converting carbon and hydrogen to ethane. The energy change combined with now bursting and take combustion, that is delta H4, that energy change should be the same as when carbon undergoes combustion directly to CO2, that is delta H2 plus, that's delta H3 plus delta H, let us change, this is H1, we change this to H2, so that we have delta H3, H2, sorry. Now, let me put that again. We have delta H1, delta H2, H3, and H4. So this is route 1, and following this path, that will be route 2. In route 2, there are 2 enthalpy changes. So that makes it quite okay. Let us confirm. This is carbon and oxygen. So we have called this one H2. Hydrogen and oxygen, we've called this H3. And so this is H1 and H4. H1 and H4, H2, just to create a good order, and H3. Delta H1 and H4, delta H2 and H3. The 2 routes are equal in energy. So let us put now the values. Delta H1 is unknown, so delta H1 plus delta H4 is the value which we have here, that is negative 1300. Now this one should be equal to H2. At this level, we need to be extremely careful, in the sense we have 2 moles. If 1 mole yields 286, what about 2 moles? So this will be 2 times negative 286 plus, we are combusting 3 moles of hydrogen, and that means if 1 mole gives, pardon that, the carbon is negative 394, so negative 394, so this will be 3 times negative 286. So viewers, let's get our calculator and work out each one of those 2 points. Negative 394 times 2 will give us negative 788. This is equal to negative 788. 88 minus 3 times 2 times negative 286 give us negative 858. Negative 858, and then we look at that. So we make H1 stand on its own side. So delta H1 now becomes negative 788 minus 858 plus, we take this on the other side as plus 1300. So viewers, key in on your calculator and work out what is delta H1. Delta H1 gives us a negative 346 kilojoules per mole. So that is very important. If we put negative 346 here, it will mean when you add that to negative 1300, that energy change should balance with the energy change of this root. So that is important. Before we wind up this question, I would like us now to answer the question, what is enthalpy of formation? What is enthalpy of formation? So we say enthalpy of formation is the heat change that occurs when 1 mole of a compound is formed from its substituent elements in their standard states. When 1 mole of a compound is formed from its substituent elements in their standard states. And that winds up our discussion in question number 1. We are going to look at question number 2, which gives us a better and a greater grip, and I'd like us to work out with the question and let's then see the working later. Let's look at question number 2. In our question number 2, we look at calculating the molar enthalpy of formation of ethanol. We calculate the molar enthalpy of forming ethanol, given that when ethanol burns or undergoes combustion, CO2 and water are formed, and 1 mole of it releases 1,368 kilojoules per every mole. 1 mole of hydrogen, when it undergoes combustion, forming water, releases 286 kilojoules per mole. And when 1 mole of carbon undergoes combustion to form CO2, it releases negative 393 kilojoules of heat energy. So the question is, we are required to use Hess's law to calculate the enthalpy of formation of ethanol. So, viewers, I would like you to pause on the video. Using the earlier knowledge learned, work out the heat change for forming 1 mole of ethanol. Bearing in mind all the concepts that we have dealt with in our question number 1. Right, let's look at how you go about it. We are going to form the energy cycle diagram, which has basis on the Hess's law. In forming ethanol, we need the constituent elements carbon and hydrogen. These are the ones in addition to oxygen, whereby we require half a mole of it to form ethanol, going by that formula. Now, 1 mole of ethanol requires 2 moles of carbon. 1 mole of ethanol requires 6 hydrogen atoms. So we shall get that from 3 moles, because every mole has 2 atoms, so 3 will have the 6 atoms of hydrogen that are required. And we need 1 mole of oxygen, which we get from half. We need one atom per molecule. We get it from half a mole of oxygen. Now, we can put the set symbols, it's no problem, and that will be liquid. So, if we label this as delta H1, we do not know the heat change for that, and that is the one we are calculating with the help of other enthalpies. For instance, when carbon undergoes combustion with oxygen, we shall have CO2. And because we burnt 2, then we shall need to show the 2 moles of CO2. When we undertake combustion of hydrogen, presence of oxygen, we shall form water. And because there are 3 moles of hydrogen, that will generate 3 moles of water. These are our products, and they have been formed through route 1. Let me now start with this route, which we are calling route 1. In route 1, we have 2 times the heat due to 1 mole of carbon burning, so negative 393. And we shall need to work out what that one is. So let us do it together. On your calculator, key in 2 times negative 393, and that should give us what value? Give us negative 786, negative 786 kilojoules. 1 mole of hydrogen gives us 286 kilojoules. What about 3? 3 times negative 286. And how much is that? That should give us about 858. 858. The negative signifies an exothermic reaction. Heat is released when that reaction goes on. So we can label this one as heat change 2 and heat change 3. So heat change 2 added to heat change 3 will be equal to this is heat change 1 and that change 1, and here in route 2 we have this as our energy change for route 2. Whereas this is our route 1. Route 1 has these 2 reagents undergoing reaction. So in route 1 we have delta H2 and H3, this one and this one. In route 2 we shall have delta H1 and delta H4 plus delta H4. Now, delta H4 is already known. This whereby 1 mole of ethanol undergoes combustion, reacts with 3 moles of oxygen, as shown there, to yield 2 moles of CO2, 3 moles of water, releasing negative 1368 kilojoules. So we shall put the respective values here. Negative 786 added to negative 858 is equal to delta H1, which we add to negative 1368. So we make delta H1 the subject of the formula. So we shall have delta H1 is equal to, we bring this on this side, will be negative 786 plus minus gives you a minus 858, but this comes to be a plus 1368. And what do we get out of that calculation? Key in on your calculator, and we expect negative 276 kilojoules per mole. Negative 276 kilojoules per mole. It is very important to note that the units of energy are the joules. We show joules in capital J. So it will be wrong for a student to show with single J. That one is not proper. It should be capital J. The K stands for kilo. It must not be capital. Just like we have milli, we have mega. So the most important is the unit joules, and we are required to find molar, and that means for 1 mole. In our equation, we developed 1 mole, that is 1 mole of ether, and that is the application of Hess's rule. In summary, therefore, we are saying Hess's rule enables us to calculate for heat changes that would have otherwise been very challenging to calculate in a normal laboratory setting. And one of them is enthalpy of formation of substances. And we are saying, as per the definition, the heat change in converting reactants to products is the same regardless of the route they followed, either route 2 or route 1. What we need to be very cautious about is the amount of reagents that we are using. Here, when we use 3 moles, then equivalently the energy per that reagent should be multiplied by 3, because in the data we have been given energy of 1 mole. The same case with carbon, we have been given energy change of 1 mole of carbon, but in the equation we are having 2 moles, so we multiply that by 2. With that, viewers, we come to the end of our lesson in how we calculate or enthalpy of formation using Hess's rule. Watch out for more on these various calculations, and kindly subscribe on the channel so that every time we upload a new video, you'll be the first one to be notified. Our channel is we have on YouTube at Steve Guitar 3660. This is where we post videos on various topics that at times are challenging to learners. We have chemistry and mathematics. Kindly do comment and tell us what you would like us to post more. With that, I wish you a very good time in your studies. Thank you.